I'll share my screen, and then I'll start presenting. It's okay. Right? Can everybody see my screen?
Yes.
Nice. Okay. So hey everybody, I'm Fred. I'm a PhD student from Duke Biomedical Engineering. With Dr. Pranam Chatterjee. Today, we're presenting master feature model sampling using the newest sampling algorithms that were being engineered in the last half a year with Stack, who is an assistant research professor at the Duke Math Department. I'm really fortunate to work with him. So today is going to be a two people talk. I'll start by motivating the projects, and Zach would later jump in and talk about the nitty gritty, math details, and then I'll wrap it up with some experiment that will have shown to prove this is useful algorithm. And yeah, this is going to be the outline of the talk. So we start by motivating, using the large language model, which is popular, everybody's using. We have all of this amazing language model here, and unsurprisingly, all of them are using this causal language modeling. So it's basically doing next token prediction. You start from a full sequence, and you just always predict the next one. And you're sampling, you just let it run, and you always predict the next, and you can generate a sequence given a prompt. So it's very simple algorithms. They simplify the learning process by removing other orders. You just consider one left to right generation order, and then this simple formulation is actually aligned with how we speak the language, right? All human languages are speak from left to right. Um, so I guess that's why the reason the simple formulation and the kind of nice para aligned with the human language enabled the autoregressive model become the golden standard for large language model right now, and has been super helpful and useful. But there are scenarios that we've been thinking about that autoregressive models cannot accomplish natively, right? So for example, there are tasks like story filling. You give the beginning and the ending of the story, and you want to fill in the body of that story. There's no way our regress model can do this natively. You can only use the beginning or code generation. This is something I suffer a lot for, not like suffer a lot, but like I have a lot of interference with. So everybody now is coding with AI, and there are kind of scenarios where you have the whole script of the code and you only have one line, then you want to revise. And in that case, you want your model to kind of utilize all of the context you have instead of just the one that before it, right? So in this case, LLMs, causal language model just cannot do this natively. And there are data, modalities, sequences that we want that this not like natural sequences that want to generate does not necessarily exhibit the left to right, the causal architecture in the data modality, right? So we care about protein sequence generation and RNA non-coding RNA sequence generation. Those sequences does not necessarily generated by the nature from left to right. So in that case, how do we model sequences beyond text? How do we model generation scenarios where we want to fill in the middle? And then we turn to discrete diffusion model or mass diffusion model. Mass diffusion model natively model the whole sequence in a holistic way, where you generate not just one token at a time, not just from left to right, but you generate from the whole context in any direction. And autoregressive model, while the autoregressive model are built to follow a fixed order, strictly left to right, and because of that, mass diffusion model has some nice properties. For example, just like diffusion model, you can do all kinds of guidance, classifier free guidance, and you can also do parallel sampling that you can generate more tokens, not just one, like LLM only generate one at a time. You can do parallel sampling that you can given a compute budget, you can reduce your sampling step that you can generate more at a time for tasks that are simple. And also, if you are dealing with a complex task, such as like reasoning task, and you want to increase your sampling steps, and then your model will spend more compute to solve this problem. So this nice mathematical frameworks is very flexible, and it gives you all kinds of nice properties you can do. Okay, Zach, I think this is your part.
Yeah, so maybe I could take over presenting. Hey, everyone see this?
Yeah, I'll stop.
Yep.
Okay, great. Yeah, so to understand the P2 framework, we still need to understand what a mass diffusion model is. So I'll describe the problem setting briefly here. We suppose we have access to some data of a form of a sequence of some length L. I'm going to refer to each coordinate as a token. This could be pixels in an image. It could be words or word groups in a sentence, or it could be amino acids in a protein sequence. And we suppose that these are sampled from some underlying distribution P naught, right? So in the protein application, we'll suppose that this is the distribution of viable proteins in nature that will actually fold. And our goal is to generate new samples from P naught, so things that we don't actually have in our data set, but that still come from that underlying distribution. And for diffusion models generally, what we do is we will have some stochastic process so that if we start at time 0 at a sample from P naught, the data that we have access to, and we flow forward to time 1, then we're going to be in some distribution that's very easy to sample from. In the particular case of mass diffusion models, that distribution is just always going to be a set of all mass states. So we want to train a neural network to be able to reverse this process, meaning that we can sample from that easy to sample from underlying distribution. In this case, just starting at a sequence of all mass at time 0. And if we simulate that process to time 1, then we recover a sample from P naught. So for mass diffusion models, and from what I've seen for all diffusion models, you suppose that you're going to evolve each coordinate independently. And in this case, we're going to use a continuous time Markov chain. So these are often encoded in diagrams like this. We're going to suppose that we start with our ith coordinate being sampled from the ith coordinate of our data distribution. Then we're going to hold in that state for some time tau with probability that tau is greater than t, being alpha t. Right, so at time 0, I won't have jumped. By time 1, I need to have jumped into that mass state. When you write out what happens for the chain, for example, when our sequence is length 3, this is what you're going to get for your forward process. So what happens is we're going to sample a sequence from our data distribution. We're going to hold for a time alpha with that same probability. And then we're going to select uniformly among the tokens which one we're going to set to a mass state. Again, after that, we're going to hold for a time tau 1 that's independent of that previous time, and select uniformly once again among the 2 remaining unmasked tokens which one to mask. And then lastly, we hold for that time, and we'll be in all mass states. So this X hat is encoding the effective process after each one of those jumps. We gain 1 mass state in a position that's selected uniformly at random. Now, what's the backward chain look like in this setting? So for the backward chain, we're going to reverse those arrows, and we're going to start at all mass states. And now what we do is we select uniformly at random among the mass tokens which one we want to unmask. But now we're not starting at our data distribution. We want to recover our data distribution once we make those 3 jumps. So how do I select what token to infill? Once I know which position I'm going to infill. So say I've waited that time, alpha t, and then I'm going to jump to the middle. How should I select X naught 2? Well, I should sample that from the data distribution given the information I have, which is none. So I should fill in this token according to the probability of seeing that token in my underlying data distribution. And then I'm going to select among the remaining 2 mass states uniformly at random. So probability 1/2, I select either. And then how should I infill, say, X1? Well, I should select X1 with probability given my second token is that x2, which I infilled. What's the probability in my underlying data distribution that I see x1 in the first position? And then after 3 jumps, I'm going to be completely at a sample that comes from the underlying data distribution. Now, no matter which arrows are selected, this is what we're calling paths, is essentially the denoising order. Which tokens do I unmask after each step? We're going to recover a sample from key knot. You can see that by writing down the definition of the conditional distribution. However, we don't have access to the underlying data distribution that I need to make sure that's what I recover a sample from in the first place. So we're going to train a neural network to try to approximate this value. That is, I input any partially masked sequence of my length, and it's going to return the probability that the ith token is whatever that token is in the data distribution, given the information from that partially masked sequence about what I know has already been infilled. So we're going to call that neural network approximation d theta. So if I'm going to sample according to this backwards process, assuming I have access to this d theta that I've already chained, what am I going to do? Well, actually, our output at each time step is I'm going to input all mask states, and then the way we parameterize the neural network is it's going to output a prediction for every single token in the sequence. But then we select uniformly at random which one to actually keep and remask the remainings. So say, in this case, with probability 1/4, we selected L. And then we do this until we've completely infilled our sequence. Now, what if we made mistakes? There's no availability for correction process here because we're trying to follow that backward chain that at every time step simply chooses a position to unmask. So for example, there's probably not a lot of English words that start with L and then have 2 letters and then S. So it's not necessarily a good choice, and we can't amend it if we're following this. We also aren't choosing the path in a principled way. What do I mean by that? I have access to all of these tokens coming from the output of the neural network once I sample from it. But I haven't used any information from the neural network or any other information of how to select which of these tokens is the best one to denoise. I think this last point becomes more clear if you look at how these are actually trained. So MDMs, massive diffusion models, are trained using the diffusion weighted denoising score entropy. What does this mean? It means in order to make sure that our sample at time 1 is going to come accurately from our data distribution, we're trying to make sure that actually the entire path of that backwards process matches the exact one. And the way we do this is we sample a random time and data point. We need some weighting by a time schedule alpha, and that's actually the only role of alpha. So this gets us this negative term here. And we're taking a log probability, so the entire thing is positive. Once we select that random time and random data point, we mask the data using a forward process, meaning each token is masked with probability alpha t. And then we look at all the mask tokens and we ask that our denoiser outputs a large probability for something that's actually representative of the data in that position. Now, you can do a change of variable argument and see that this is actually equivalent to the following expression. So what am I saying here? I'm saying that we're going to select sigma, that is a path sampled uniformly from all the possible permutations of paths. And then I look at the resulting sample taking that path of my approximate backwards process, and I take the KL divergence. It's a measure of the difference between my true data distribution and the output of the neural network. So what does this mean? We're trying to minimize the average of this difference among all paths. Okay, but if I select a path uniformly at random, all my paths potentially a priori could be perfect except for the one that I selected. So even if I made sure that the Shannon entropy, the loss minus the Shannon entropy was epsilon, it could be as bad as epsilon times L factorial in this path that I selected, which of course is going to be enormously large. That's all to say, training on that average among all possible paths doesn't guarantee that actually the KL divergence on all paths is going to be small. Not all paths will be created equal. So how do we amend, say, this case with L equals 3 in the P2 formulation, right? So what we do is we first introduce these red arrows that are our correction steps. That is, whereas previously, once I unmask, say, the token in position 3, that value is going to be fixed in the vanilla backward process. Whereas in P2, we allow to remask that while still making sure that after 3 steps, we're going to denoise the entire chain. Moreover, instead of selecting the position uniformly at random, we introduce our planner G theta. And that planner takes in the information, 1, from the state I'm in now, the partially masked sequence, and 2, from my prediction from my denoiser of where to go in the next sequence. So in this way, we're able to use actually the output of the denoiser and potentially the logits of the denoiser to determine which choice is the best. So here, if Gj is giving the probability of changing the jth token, if G3 was extremely large, that's saying, oh, I made a really bad choice at this sampling step for how to infill my third token, and I should remask it. We can also derive an elbow. I'm not going to talk through all of these 3 terms in general. I will just say you could potentially fine-tune a given MDM denoiser with a planner using this elbow. If you minimize this, this is going to it's an upper bound for how much your sample will change from the data distribution in KL. And we have 3 terms. We have, I'll talk about the last one first. This is exactly the same as the denoiser loss. So this is asking that the denoiser is able to infill the correct token properly no matter what path we choose. The second term here, this is the unmasked position planner loss. What does this mean? This means that for a position which is not masked in my partially masked sequence from my sample of my data, get a sample from the denoiser, and then replace the ith token with the correct token from the data. So I want to make sure that 1 minus G theta is going to be small, so that G theta, oh no, other way around. I want to make sure that it's large so that G theta is small, meaning I'm not going to try to correct a position that's already representative of the data distribution. And similarly for masked positions, I'm going to want to take a jump in a position that is representative of the data distribution. So if my ith token is masked and my denoiser is suggesting a token that is representative of the data distribution, then I should denoise that position with high probability because it's a good place to go. And I think I'll let Fred take it from here.
Okay, nice. Okay. Let's see, present now. Okay, wait. Sorry, I gotta follow all the way down. Okay. All right, so yeah, Zach gave a really nice background about all the math here. So based on that motivation, then we decided to decompose the planner into 2 components. Because given a time, we have XT, the partially masked sequence, and there are 2 types of token in that sequence. There's masked token that we want to unmask, and there are already masked token that we want to possibly keep or remask, right? So and based on that, we have these 2 planners that one planner is basically for all the mask tokens, and then they're going to tell me the likelihood to unmask it. And this is a unmasked token planner, which is going to give me the likelihood for a unmasked position and what's the likelihood that I'm going to keep this unmasked tokens. And we later realized that you can add this stochasticity term, eta here, to control, in a way that basically what we found is when you try to do sampling, and then you can control how much you want to remask. And we have this eta term, and they can trade off this the planning between the masked position and the unmasked position. And this term is starting from 0 to positive infinity. And if you go higher, then you're gonna introduce more stochasticity into your denoising process, which means you would see that the token being unmasked and then remasked, unmasked and then remasked. You'll see a lot of unmasking, remasking process in that chain. That meaning the model is doing a lot of correction if you increase this term. And then I think it's particularly important if you're doing like challenging reasoning tasks. For example, you're solving like a math problem and you realize that you have made a lot of mistakes in the previous step, then you can have a higher eta value, and then the model will kind of remask a lot of predicted tokens, and then you're gonna spend more time in correcting your sampling. So overall, by integrating this planner into our sampling process, we will basically follow in the same sampling strategies, right? So imagine if you just do ancestor sampling, which you basically randomly choose a position, unmask, and choose a next random position, unmask until you run out of all the mask positions. But in the P2 planning sampling process, what you have is you're gonna first use the planner to choose a position, and if that position is a mask, then you're gonna unmask that. And if that position is an unmasked position, then you're gonna set it to mask. And the planner is just gonna tell you what position you're gonna choose. And then you purely just rely on the denoiser to make that prediction of what you're gonna predict it to be. And this is kind of separating the two jobs to one to planners selecting positions, and one to the denoiser to make the prediction. So this is a nice algorithms that kind of really simple you can do, and this is the essential sampling process where you only just pick one. You select the position by the planner. For example, you start from 0, and your denoiser will make a prediction, and your planner will tell you what positions are good. Right here, we're basically using the value to rank all the positions. And since all the, at time 0, all the positions are mask tokens, then you're going to choose the one that was the highest likelihood, and you unmask it. And at the second step, you're going to choose the last one because it has the highest likelihood, except for the first one, but it is already unmasked, right? And particularly, I think in the step 2, where you have the last S, which is unmasked, but it has a very low likelihood. And in that case, you're going to set it to mask, and you're going to choose, except for the last one and the first one, because one has a lowest likelihood, and the first one has a kind of high likelihood. You're going to choose from the rest of the mask positions, and you're going to select one to unmask. And this is how the past planning can amend all the mistakes that you have made previously. So by using these simple algorithms, we can instantialize it to different practical planners, right? So in our paper, we basically introduced 2 planners. One is the self-planning, the other is BERT planning. And interestingly, because given the fact that past planning is such a simple algorithm, but it's still not necessarily practical for most of the cases where you have to train an external planner, is less likely to be the case. So we have the first self-planning, which does not require any external planner. You can just use the denoiser itself as the planner. So we basically write down the formulation where you have the mask planner, which is where you have this denoiser, right, D, and which predict a position, predict a mask position. You can use it for mask planning, which is basically gonna suggest positions for positions for the mask position. And you also have the a mask planner, which you also are going to use the denoiser for it. And I'll show you this. This is actually pretty useful in most of the cases. And another scenario is, even though you don't have to train a dedicated planner, you could use a BERT which is readily available in most of the scenarios. For example, in protein sequence generation, you have ESN2, which is just basically a BERT. And in language, you have all kinds of BERT that has been trained, I don't know, 5 years ago. So BERT is another planet that's pretty available. And we basically, in the BERT planning, we for the mask planner, we're going to stick with the denoiser itself. And for the unmasked planner, we plug in the BERT to make a planning selection for the unmasked positions. There are just 2 special cases of P2 we kind of proposed in the paper. I'm pretty sure there are other available planners that we can explore. Yeah, this is just things. And so I did some simple application for this, basically trying to elucidate the design space of a P2, since we have basically 2 terms in this table, right? So we can do stochasticity control by tuning the eta. We can increase or decrease the remasking in the reverse chain, and we also have different choice of planners in the in our box, so that we can just plug in different parameters and see how it performs. So I want to show you let's find the greedy ancestor sampling. So okay, ancestor sampling is basically doing ancestor sampling, but they're using the model confidence to select the token instead of randomly to select the one with the highest confidence. It's called greedy, but you still cannot amend the mistake. So we have them right here. There's no stochasticity control, so you can stick. You stay with stochasticity of 0, and also this is the point I forget to label in the paper. But basically, this is the ancestor sampling, the vanilla ancestor sampling, where you don't use even the confidence, and you have no stochasticity control, and you start from here. And then what you can do is you tune the eta for those 2 line, right? This is the orange line, and this is the green line. You tune the eta, you can see the performance can kind of fluctuate a little bit, and particularly if you can, enable eta, right? So from 0, there's no stochasticity, there's no remasking. You're gonna see the performance get really bad. But as long as you open it, enable it, you can see some performance gain, and then you kind of saturate it, right? Later it becomes like a parameter tuning thing that you want to find the optimal parameter. But the punchline here is, as long as you enable the remasking, you can get a nice performance gain. And in particular, if you compare the 2 curves, one is the self-planning. So the orange line is basically self-planning, where you just use the denoiser itself to plan for the sampling. And the other, the blue one is the one that uses the BERT planning. And you can see by integrating a BERT model, you can, it functions really similar to self-planning, but there are times that you can get a better performance. And this is how the kind of the design space you can explore in P2. So we did a bunch of experiments. One is in protein. So in protein sequence generation, you basically unconditionally generate protein sequences, and then you feed into some protein folding models like ESN-fold or AlphaFold2. But AlphaFold is kind of expensive, so here we stick with ESN-fold. And you fold those sequences, you would get like 3 values. You get PLDDT, PTMs, and PAE. Those are confidence matrix that the folding model gives. That tells you how confident the model is about the given sequence. And the higher, the more confident, the higher quality of that sequence you provide to the model. So in that case, we're using those confidence matrix to evaluate the quality of our generator, right? So we have these 3 terms here. And then I further combine these 3 terms to propose like foldability, where you have 3 thresholds for PLDDT, PTM, PAE, and you only pass if a sequence that has passed the threshold of these 3 individual matrices. So this is a more strict matrices, and this is the one that we mostly follow. And also then you would have the entropy and diversity, which basically tells you if the model has some mode collapse, right? So if you generate something that's has low entropy, that means you basically generate a sequence of the same token, or if you have low diversity, then you basically generate a bunch of sequences that are all the same. So these two matrices are used to monitor the mode collapse of our model, and we compare with all the existing state-of-the-art, particularly we have ProGen that being proposed a couple of years ago as an autoregression model, and they have 3 sizes. I think the largest one is like probably 2 or 3 billion, and you have ESM3, which is I guess 2 billion or something, 2 billion, 3 billion. We have EvoFlow, which is another diffusion model for sequence generation, and we can see. Also DPLM, I just want to mention, which is considered as the state-of-the-art baseline here. And we mostly just using DPLM, the master diffusion model, and adding our sampling algorithm, we can basically get like a nice improvement across all the matrices, including 150 million and 650 million. And then we have a nice, we preserve a nice entropy. There's no degradation in our sampling, and we can even sometimes increase the entropy. And we have kind of pretty much the same diversity here. So this is the result on voting generation, and we also fold them into nice shapes. There are more figures in the paper, and also did the same thing for RNA generation. We have a couple of waysides. One is this BERT. This is a kind of just a basic language model, 150 million, 650 million. And then we train a mass diffusion model on non-coding RNA sequences. I think it's from like RNA Central was probably about 20 million sequences. We trained the 150 million version, and then we kind of apply different sampling algorithms by using, RDEM sampling and the P2 self-planning and the P2 plus the planner from a BERT, which is the randomal 150 million version. And we can basically see, so we also have like native sequences as a control here. So if you take a look at the control and the foldability, like the folding kind of matrix PLDT of native sequences is actually not very high, and that's just because RNA is sometimes less foldable. But given the current model we have, so we additionally monitor a couple other matrices such as the MFE and GC content. We can see by using the P2 self-planning, we can kind of out of box improve the sampling algorithms. The sampling quality, and then by additionally using the planner, we can further improve the foldability, foldability of the generated RNA, and also surprisingly have better, has a nice entropy here. There's no much of degradation in our generation, but if you just run a BERT model for sequence generation, we get like really terrible entropy here. And also fold a couple RNA sequences here. You can see a nice topology. Yeah. And then lastly, we did some interesting stuff in language and code generation, because this is, I think, where people care in just general machine learning community, where you want to see if mass diffusion model can rival the state-of-the-art, the causal language model, the LLM can become the next generation backbone of the LLM. So we have a couple tasks in language generation. One is this lambda, which is basically question answering. So you give it a bunch of question. No, sorry, this is not question answering. So so basically given like a text, and then you want to fill in the last word in this text. And then you have a GSM AK, which is a high school level of math, and which is very simple. I think we can all accomplish this, not just Zach. We also have the TriQA, which is question answering task, where you kind of, if you know some facts, they're asking about some facts, and you're supposed to know that and answer it. The last one is, this one is a story filling. We have shown you before. You want to fill in the story in the middle, and this is the code generation. I think this is a college level, which I have a hard time, coding this. But overall, this is a kind of challenging and typical language generation task. We basically use the existing benchmarks they have people have been using in this area, and then we compare with some of the famous model, I guess. For example, we have GPT-2. You have a llama, tiny llama, which is a community reproduction of the llama, and we have some other existing diffusion model, SEDD, and DiffGPT, and played. And we also have the Llama 7 billion, and also we have the pre-trained. Sorry, we have the pre-trained Mass Diffusion model 1 billion, and we have Deep Llama, which is another 7 billion model. And we in this five benchmarks. I think in the first one we are largely worse than Llama because, for example, you see Llama has like 45 accuracy, and we have only like 20%. And I think this is largely because this is a question answering task where you have to memorize a lot of facts, and the memorization of the diffusion model right now is not well studied. So kind of the limitation of the mass diffusion model. And then if you look at Lambda, which is basically performing the same, like within each other, but like doing much worse than Llama 2. And then if you look at the GSM 8K, which is this math reasoning task, you can see by using the P2 sampling algorithm, we can enable the mass diffusion model to outperform like a 1 billion mass diffusion model to outperform a 7 billion Llama 2. And this is kind of surprising to me. And this kind of highlights the fact that a mass diffusion model is probably very good at sampling task where, probably pretty good at reasoning task where, it requires a lot of thinking and kind of a remasking. And this is what people right now like care about the most. They want their GPT to be able to reason. And I feel like mass diffusion model can just do this out of the box. And we also have this story and filling, since the mass diffusion model can just fill in the middle out of the box. So we can easily just get a higher, much better performance compared to Llama. And further, by using the P2 algorithm, we can even improve it on top of the existing Deep Llama 7 billion. And lastly, we have the code and filling. And unsurprisingly, this is a challenging reasoning task, and this is also a filling task. So diffusion model can just do much better than Llama, where it has like 1.7. Diffusion model natively have something above 10. By using the P2, we can further improve that score. So this is pretty nice. And also I want to kind of circle back here. Even though in these two kind of common sense tasks, the diffusion model is doing pretty bad, but by using P2, we can still kind of slightly improve that. But yeah, that's the kind of results on language generation. Also, we want to kind of talk about the elbows that we derived. So we have this the 3 elbows for the planning, for the 2 planners and the denoiser, and then the elbow can give us the mathematically backed evaluation of the planners, right? So we have the elbow, and if the planner has a higher elbow, well, I can't say higher, but if planner has a worse elbow, which means this is probably a terrible planner that you don't want to use, right? So we can just plug in, if you have all kinds of planners and you're wondering which planner I should use in practice in my task, what you should do is just you take a subset of your data, and you plug in to all of your planners you have, and then you compute the elbow and see which one is lower. And if you have a better elbow for a planner, then you should stick with that planner. And this is very nice for our elbow to mathematically enable you to do this kind of evaluation of a planner. And here we did this for our protein sequence generation. So we have ESM2, which is a BERT, and they have different size of the BERT from 8 million to 3 billion. And what you want to do is you plug in your data, you plug in the planner into sampling, and then you compute the elbow, using a subset of protein sequences, and then you can compute the elbow for the unmasked positions and the masked position. And surprisingly, 2 facts here. One is all the planners you have, regardless their size, even the smallest one, 8 million, have the similar elbow compared to the biggest one, 3 billion. This is very interesting. So what it tells you is you actually don't need a powerful planner to do sampling. Maybe just use the 8 million model to guide your mass diffusion model. And you can see on the figure on the left, all the curves here are basically the BERT planning, and you can see they're all exhibit the same scaling curve, right? Where you have, you tune the temperature, you have different entropy, and you see like the flowability kind of scale up and down. You see, regardless of the size, it has a similar performance across the different temperature and entropy. And the fact too is the self-planning, which is the curve right here, is surprisingly doing much better than using the BERT planning. And so before we do this table, which this is what we have done in the last of that experiment, we first have this figure, and we kind of puzzled why self-planning is doing much better compared to using the BERT planning, right? It doesn't even introduce an external planner. So we compute this whole table, and we'll take a look at the elbow here, and then we realize the reason why self-planning is doing much better is because it has a better elbow. Well, we can't explain why this is better elbow, but given the fact it has a better elbow, it makes more sense that it has exhibited better floatability here. So overall, we just want to highlight the message here. You can plug in the elbow, you can evaluate your planner. So this is a nice thing about P2. And lastly, I just want to show P2 is efficient, and here we kind of tuned the sampling steps, as I mentioned. If your task is simple, you should use less step and get similar performance. If your task is hard, you use more steps and you use more time. And then we compare different sampling algorithms. We have the sensor sampling, we have the BERT planning, and the self-planning. And you can see, regardless, as long as you use P2, you get like a nice scaling. If you use BERT planning, you get your scaling is probably much better. And we also compare the sampling times, compare the sampling time versus the sequence lengths. When you generate sequences of 1,000 tokens, you would get like, supposedly you get like, you're gonna run more time, but you can see, compare with sensor sampling, which you can't even find in this figure, but it has in it. For example, you can see over here, the difference between the runtime difference between the ancestral sampling and the P2 sampling is marginal. And the reason is because, first, if you are using self-planning, you don't introduce external model. So your inference is basically the same as ancestral sampling. You're basically tuning some of the parameters there. You're not running extra stuff. So the sampling time is supposedly to be the same. And if you're using BERT planner, we introduce external planner. In that case, you have some a little bit overhead because you're going to run the planner model, which is another neural network. But the punchline here is it's an 8 million BERT. Just like what we have shown you, the smallest BERT model can effectively guide your generation. So in that case, the 8 million model compared to denoiser, which might be 1 billion or what we have done is 650 million and 1 billion and 7 billion. There's basically no overhead, no noticeable overhead in your sampling. So overall, by introducing the small planners or self-planning, P2 can be really efficient in practice. So yeah, overall, we have done all the experiments. We have some nice visualizations of the RNA structures, secondary structures. We have nice protein generated. Those are from 200 to 800. Those large proteins can be generated. So code is available. We just organized it a couple of weeks ago, and we released it on GitHub. And we have examples of protein generation and text generation, and also been working on some more modalities such as RNA. Yeah, and thank you everyone and for coming here today. And I want to thank to all the co-authors who've been really helpful to the paper and to the experiment. And also I have a bunch of amazing people advising me, and they've been giving me nice guidance along the way. I want to thank them. And yeah, and I want to thank everybody. I think that's the talk.
All right, thank you so much.
Yes.
I'm going to stop this recording now and start a new one so we can go into Q&A.